The recording. Thanks. And I'm happy to announce Mikhail Majesinsky. He is speaking in our seminar today about omega fields, exponential function, and surreal numbers. Thank you so much, Mikhail.
Thank you very much for your introduction and for the invitation to talk. So, as we just mentioned, this talk fits pretty well between both programs at the fields, I think, because the main, first of all, sorry, I will speak about a joint work with Alessandro Salma and Vincenzo. And it's about two main objects that are of interest to us, namely surreal numbers, as I indicated by the title. More precisely, surreal numbers with exponential. And the second kind of objects, so let me just recall that surreal numbers were defined by Conway in the 70s and the exponential by Gonchori in the 80s. And the second kind of objects are the so-called kappa-bonded power series fields. Also with exp. So these were introduced by Salma and Sheila in 2007, if I'm not confused, or 5 maybe. Which are of the same flavor as log exp series, xlog series, trans series. So I said it's connected, of course, with the ongoing program at the fields. Namely, there are two courses that are about these topics. So the first one about surreal numbers is given by Alessandro Berarducci and Vincenzo Mantova. And the second one about trans series more specifically, and also Hardy fields, is given by Lau. So I will take this occasion maybe not to go too much into the details of the given construction of these two kinds of objects, so that because it takes long. In fact, I also gave a talk about 1 year ago at the Séminaire Général de Logique in Paris, where I gave an introduction to this topic. So we could see this also as a kind of follow-up of this talk I gave there, if you attended. And so in the present talk, I will speak more specifically on what we call omega fields within this context. So let me put the setting. So we consider a real close valued field, or real closed field endowed with a convex valuation. Or you can view it endowed with the corresponding map. Recall that any such field always admits what we will call a group of monomials. What is it? It's just a section of this map. So let me denote it by M. So it's a submultiplicative order abelian group of the invertibles in K. Then we just think that the value group is a divisible ordered abelian group. And then this M can be thought of as the equivalence classes. Well, I don't spend too much time on this. I guess it's classical for most of you. So we say that K is a omega field if there is an isomorphism between this monomial group and the field itself. Let me put the arrow. Yes, no, in this direction. M times. Okay. So the notation we introduce is this power notation because it's a morphism from additive to multiplicative. So it's kind of an exponential map. But we'll see, well, of course, it's not the usual exponential in the real sense. Why do we take this specific notation with an omega as a formal variable? It is from Conway's original definition in the context of surreal numbers, because this map is a generalization in this context of the usual ordinal omega exponentiation. So we call this map the omega map. Let me right away compare it with the usual exponential map so that we have already a certain link between both. And the notations. Okay. Let me just say a few words on these motivating examples, the surreal numbers. Again, you can have more details on in Alessandro and Vincenzo's course, or if time permits, I will give more details at the end of the talk, but we'll see. So there are three ways of viewing surreal numbers. So the original one from Conway is a recursive definition in the style of Dedekind and von Neumann. Dedekind for the real numbers, and so in terms of cuts, filling the cuts, and von Neumann as he defined the ordinal numbers. The second point of view is a full binary tree. And this one is due to Gonshore. It was also a bit indicated in Conway's work. And the third way, which will be the most interesting for us, is to view surreal numbers. So, sorry, I denote the class of surreal numbers. It will be a proper class, not even a set, as NO. And NO can be viewed as generalized power series field, but be careful with support of this power series, which are sets, which cannot be proper classes themselves. So that's what means this ON here, a sort of bounded power series field. We will see in a minute what we have in mind by this. So let me just put the notation. So for any surreal number, there is a unique notation, decomposition, in fact, as a power series. So with Ri being real numbers, so here non-zero, and AI reverse well-ordered sequence in NO. So this is a point of view which will be the most interesting for us, and which shows that the rich structure that NO has. We'll talk about this maybe a bit later. So what is obvious in this formula that I highlighted now is that we have such isomorphism. Because this omega map is meant to be order preserving, so it's an isomorphism, and between NO here and NO here. Just to give a hint about the sense of this omega map in the context of surreal numbers. So as we said, it's a group of monomial. So a group of monomial, in this context, the valuation is a natural valuation, the one corresponding to Archimedean equivalence classes. And so in terms of doing a recursive definition of this omega map, you can define, I hope the notation will be pretty obvious. You define the omega exponentiation of a surreal number A in terms of previously built surreal numbers, this AL, which is to the left of A, and AR with AR to the right of A. And this, as you might see, N runs over N. So you have here the simplest element that fills the gap between two previously built monomials. So it indeed realizes a new Archimedean equivalence class. So this is the way that you build this omega map in the context of surreal numbers, and then you show that this is really an isomorphism of ordered abelian group and so on. So as I said, if time permits, I might give a bit more details on this. But this is the motivating examples for us because, well, as you might already know, this field of surreal numbers is a field with exponentiation, also derivation, partial composition. It has many good properties, reflecting the one of, well, real non-oscillating functions in the differentiable context. Okay, so let me now speak a bit about the other objects, so the bounded power series field. So Kurman and Shelah. So here we consider K to be a real analytic and exponential field. You can take K to be R. And we consider a given group of monomials. When I say group of monomials, it's just meant to be a priori multiplicative order abelian group. And we consider kappa to be a regular uncountable cardinal. Then what we denote by K of G subscript kappa is the subfield of generalized power series of the following form. With I less than alpha less than, so for indexed by an ordinal, which is less than kappa necessarily. Of course, with mi in capital M, reverse well ordered. This is a condition to have really a field of power series, and Ri in our field K. Here non-zero, because I just meant this to be an enumeration of the support of the power series. So these objects were introduced by Saron and Salma in order to provide different models of real exponentiation within non-Archimedean context. Oh, sorry, what did I write? Non-isomorphic models. But all being isomorphic in terms, well, as ordered fields. I should say as analytic ordered fields. Analytic ordered fields. So this is obtained by building in a recursive way specific group of monomials. So these models are given by specific group of monomials. Let me just give the key formula to build these objects. So given a power series, you can always write it in a canonical way as a monomial times a constant, or here we will consider a positive constant. So, and this being what we denote by neglectable compared to 1, which means the valuation is strictly positive. Sorry, no, epsilon is infinitesimal. So the formula for the log is given by a power series which will be purely infinite in the sense that all its monomials are with infinitely large, the monomials appearing in the support, the constant term, and the infinitesimal part, which belongs to the maximal ideal of the field. Oops. So this is a classical formula, the usual one. So we have to give each, it's a necessary formula, it's not even classical. So the log on K is restrict to the log on small k for constants. On 1 plus epsilon, it is the analytic formula which can be extended in this context to infinitesimal elements. This extension in the analytic case, you can view it in the Van den Dries McIntyre marker paper. And the log of M0 is the crucial guy that we need to now to define, to give a definition in logarithmic terms. Then the formula here will be of the following form. So given a certain enumeration here, I will explain where it comes from. Oops. Where the monomial M0 is viewed as a formal infinite product of particular monomials raised to some power, Ri. And here also viewed as a bounded group of monomials. So this is the so-called Hahn group over gamma. Gamma being a chain, totally ordered linearly ordered set. And the monomials, so always are objects of the following form. So reverse well-ordered products. Of elements of the chain and formally merge as a formal product. So let's denote more generally this kind of groups, H gamma with subscript kappa to indicate, to recall that they are kappa bounded. And then the crucial argument there is to build inductively, starting with gamma 0, some random given linearly ordered set, to saturate it so that you get a new chain which has the property to be isomorphic to this hand group. Sorry, I should have written this. So to the part bigger than 1 of this hand group. So this is the kind of idea that we will exploit in the context of omega fields. So the first thing that I want to present, so that this notion is as an interest, of course, is to how can we build omega fields? Are there other examples than surreal numbers? In the same vein that there are examples of exponential fields and so on. So first theorem I want to state, so as I said, K here a priori K here just needs to be a model of the restricted analytic function, the expansion of the real with restricted analytic functions. Then we show that we can find a group of monomials always for any regular and countable cardinal kappa. I hope the statement is clear. So let me give a sketch of proof, which gives also, which rings a bell with the Kuhlmann-Scherer construction. So it is in 2 steps. First step, build a chain gamma, which is isomorphic. Let's denote the isomorphism by eta to the full hand group. Well, not the full, but the kappa bounded hand group, not only it's bigger than 1 part. And the second step, so given that, we define K to be the kappa bounded. Let me call this guy M kappa of kappa bounded series over this M kappa. And we can define an omega map in the following way. So here, any element A can be written as a sum of, voila, in its power series form. So we will define the image by omega of this element A as the following monomial. So what is the link between these elements that M gamma I, Mi, sorry, is the image is equal to the image of gamma I. So gamma I is an element of gamma. More explicitly, in particular, omega eta gamma is defined to be m gamma. So this shows that you have you have to check it, but it is an explicit version of the isomorphism between the field itself and the group of monomials. Then so what I want to explain quickly is that how we get this isomorphism here. So this is so we adapt Kuhlmann-Scheller, and the idea is to use the functor between chains and ordered abelian groups, which is given by this bounded Hahn group construction. So the idea is to start with a given gamma 0, a given embedding of gamma 0 into the corresponding Hahn group. So just for the sake of notations, so if you want an explicit example, just take, for instance, this value. It's just sending the element gamma to the component of the Hahn group indexed by gamma. But we can find other embeddings more complicated, composing with a shift on gamma if possible, or with different possibilities. Oh, there is a jump here. Oh yeah, no, sorry. So then we want to expand this gamma 0 to obtain this gamma. So we will do inductive expansions. And let me give the general step. So for an ordinal alpha, we assume to have the same situation, an embedding. And then we go to the next step by defining gamma alpha plus 1 to be an isomorphic copy. Well, the pullback of an isomorphic copy of this guy, which is a complement which includes gamma alpha. So you can think of this as a forgetful functor, because this to the right being an ordered abelian group is a linearly ordered set. And then take another embedding. No, it's an alpha here, sorry. And again. So so this is for a successor ordinal, and for limit ordinals, we just take the union. Let me move this a little bit. and we continue until we reach gamma kappa for the uncountable regular cardinal. And we show that this is isomorphism. Okay, I hope I dare to put a square here, hoping it's clear enough. If you have any question, you don't hesitate to ask. So this shows that we have many, in fact, explicit examples, because here I just began with a random linearly ordered set. So you might have many things, and also you might have many embeddings here and at any step. Okay, so the second part I want to mention is that we show that any omega field of the given form, bounded series field, in fact admits not only one, but many log-exp structures. With some of them providing models of T and X, others not even or minimal. So this shows that it's pretty flexible construction. Again, I'll give a sketch of proof. So the key objects that we will use is chain isomorphism, underline chain, between the big field itself and its positive part. So let's call this isomorphism H. So this is really, this exists always, and there are many. I will give examples in a minute. Why are we interested in this guy, this kind of guy? Because we will rely on the following key formula, which highlights the link, the deep link that might have between an omega map and a log. We will express it in terms of the log better than exp. So for any element of the field, the log of omega omega to the A is equal to omega H of A. So what does this say? It says that omega is almost an exponential, but twisted. Because when composed by log, you lose a step in the omega tower, but there is a twist. So it's not the same. About this double omega guys, let me just give, for the sake of intuition, that for K being R or any Archimedean field, these guys represent the multiplicative Archimedean equivalence classes. So also key objects, or in other words, it encodes the rank of the natural valuation. So this is why these guys are key key objects. So why is this a key formula? But then for any monomial, M, you can write it as omega to the A by this isomorphism omega for some A in K. But then A itself can be written as, well, it's a power series. So you just write it as a power series. But then each monomial Mi is itself a monomial in corresponding to some guy AI in K. Now this will help us to provide a formula that makes sense, that works. So our monomial M is then written as omega power sigma of Ri omega to the AI. And then we'll define the value of this guy. So you see it's, well, I can give another step here. You can view this as a formal power product like this. Then you define the log of this formal power product to be the sum. These are infinite things, formal, but still they make sense in this power series field. And now we use the previously introduced formula using this twist H. Okay. Third step, how do you define the log on the positive part of the field? As we did before, you write your element as a canonical product, and you write log of A as B. If I'm not confused, I wrote it this way. As before. So now the only thing that I did not justify so far is that how do you get such H to be an example of isomorphisms between K, and its positive part? Well, easy examples. Take H0 of X to be X plus 1 for positive X and 1 over 1 minus X for negative ones. Well, another one. Of the same kind. And so on. many examples. So the key point to complete the statement of the theorem is the remaining part. When are these guys, these logarithms, and therefore the corresponding exponential, when are they hominimal and when are they not?
Mickaël, just wanted to mention it's 5-1.
Okay.
Yeah.
Oh my God.
Yeah.
Yeah, thank you. This characterization will rely on the fact which follows from Rosser axiomatization and Van den Dries McIntyre marker. Here we can take K to be, I should have said this before, maybe I forgot to say, okay. So this field, such bounded series field, will be a model of T and X if and only if, well, given the formula that I gave before for the log, the analytic log on the infinite, on the bounded part, what remains to be checked is the growth axiom. Here we write it in terms of x at infinity. So this growth axiom scheme. So then this translates as a specific property of this map H in our context, that H of x should be dominated by omega to the x for any k in the field. So here, this is not the case for these two examples that I give here. A priori, then you might have omega functions that will not have this property for these two H0 and H1. But what we show also is that by a bootstrap procedure, we built an H3 map using, oh, why did I call it H3? It should be H2, sorry. Using H0 and H1, which really have this good property. Well, and we know that there are because of in the context, for instance, of surreal numbers. Maybe I will stop here because, well, time is done and it's a good, or maybe just let me mention quickly the last theorem that gives the rest of the picture. Again, take your field to be a bounded power series field. And this time you assume that it's endowed with a log, as in Kuhlmann-Schella's construction. Then there is a condition so that your field can be an omega field, and which is a non-trivial condition. You need that your group of monomials is isomorphic to its bigger than one part, or isomorphic in terms of chains. And then in this case, there is an H map such that, well, I leave the rest of the statement. You know what I mean, I guess, if you. But there is really an example and many examples of logarithmic kappa-bounded series fields that are not omega fields. So this is really an extra property which gives specific models which are of the flavor of surreal numbers. And let me stop here. Thank you for listening.
Thank you, Mickaël. Let's thank the speaker. All right, so it's